right, so for these next few examples, we're just going to set up our integration strategies, but I don't want you to integrate them. So here, looking at our first one, definite u sub going to happen right here. We're going to have u be our sine of x. That way our cosine x dx will be part of our du. So the derivative of sine of x is cosine x dx. So this will integrate u squared du. Over here, well, we have sine squared x, cosine squared x dx. This is our half angle identity. So we'll have to substitute both these in, factor out the halves, FOIL this together, and if memory serves me right, I believe we did an example of one of these back in sines and cosines and powers. Here we have sine is to an odd power, so we're going to take one of these sine x factors, move it over to our dx. All right, and that way u will be cosine of x. The derivative of cosine of x is negative sine x. That's why we want to remove one of our sines over to the dx as our factors. And then our sine squared will turn into 1 minus cosine squared x. So here's the sine, extra sine factored away, so leaves me sine squared x, move it over here. Now with that du, remember we'll have to factor the negative over, so it'll be a negative integral. 1 minus cosine squared x becomes u squared. This cosine squared x becomes u squared. And now you can go through the integration technique. Integrating the inverse tangent of x dx, this is going to be an integration by parts. So the inverse of tangent x is my u. Dx is my dv. If you take the derivative of the inverse tangent of x, you'll notice on your sheet that it is 1 over x squared plus 1 dx. And if we integrate dx, we're just going to get x. So integration by parts, x times my inverse tangent of x minus the integral of x over x squared plus 1 dx. And now you can do a u substitution. So u would equal the x squared plus 1. Du is going to equal 2x dx, the derivative of x squared. So we'll factor a half over by the du, divide over the 2. Half goes in front of my integral. And now I have du, x times dx, that's my du, over u. Then you can integrate this part and then subtract it and add your plus c. Example E, this is definitely the square root, perfect square, minus or plus another perfect square with a variable. This is going to be my trig substitution. So 9 minus, that means 9 is 3 squared, so 3 is on my hypotenuse. I want to put x across from theta. We'll put the square root of 9 minus x squared adjacent to theta. So sine theta equals x over 3. X is going to be equal to 3 sine theta. Dx is equal to 3 cosine d theta. We'll make our substitution. So once you substitute in and clean everything up, you'll integrate to 9 sine squared theta d theta. And again, you'll have to bring your half angle identity into play. For f, definitely a partial fraction decomposition. So if you factor the bottom, you're going to get x plus 2 times x squared plus 1. You'd have to do factor by grouping. So a over x plus 2, bx plus c over x squared plus 1. Then solve for a, b, and c, and then integrate each one individually. Now, if b happens to be a 0, where you have a constant over x squared plus 1, you can use your tangent identity for that one right there. Otherwise, use u sub because your x will be 1 degree smaller than your x squared. For g, tangent to the fifth, 2x, secant to the fourth dx dx. Both techniques will work well, but the one with the least amount of work and is most efficient is to take secant squared dx and save it for a du. Let your u equal the tangent of 2x. That way your du is going to be equal to 2 secant squared dx. And don't forget, take the derivative of 2x. And multiply it to the 2. Don't forget your chain rule there. So there's my secant squared of 2x with my dx. I'll take my other secant squared of 2x and change that to tangent squared of 2x plus 1. And then we make our substitutions here. So we're going to have u to the fifth times u squared plus 1. Here's my du, but remember, don't forget you have to divide over the 2. So there'll be a half being factored out front. And then we'll just multiply into u to the fifth and integrate normally. H, kind of sneaky here. It's a u sub. We're going to let u equal the square root of x. And I'm going to let u be squared, and I'm going to square the square root. So u squared is equal to x. And now I take the derivative to get to dx. I had to get rid of the square root here. I did not want to take the square root of x to the 1/2 power, because then I'm going to have an ugly looking x with my dx. I needed the dx to be all by itself. So squaring both sides gives me x by itself, and when I take its derivative, I get dx. So we substitute everything in. So 2u du, and then there's my e to the u. So this all gets multiplied together, and now it's going to be an integration by parts. So u is u, e to the u du is my dv, the derivative of u is du. If I take and integrate e to the u, that's just e to the u. And so now that's 2 times uv, there it is, u times e to the u, minus the integral e to the u du. And if you wanted to integrate that real quick, that would just be minus e to the u plus a c, and then distribute the 2. All right, example I, integrate natural log of x dx, integration by parts. ln of x is u, dx is dv. If I take the derivative of natural log of x is 1 over x dx, integrate dx is going to be x. So x times natural log of x minus x times du, 1 over x dx, the x's cancel. So I can integrate that to just be x and plus a c. J is integration by parts as well. Now my u, that's going to be natural log of x. Remember your LIATE rule. X will be times my dx. Integrate that will be x squared over 2. And the derivative natural log of x is 1 over x dx, just like it was over here. So put it in our integration by parts. U times v, x squared over 2 times the natural log of x, minus the integral of x squared over 2 times du, 1 over x dx. I can cancel the x's, factor out a 1/2, and integrate accordingly. Natural log of x over x, this is a perfect u substitution. Let u be the natural log of x. The derivative of the natural log of x is 1 over x dx, so your x is in the denominator, that's 1 over x. Perfect u sub, integrate u du. Integration by parts over here. We'll let u be ln of x. X squared on the bottom, let's call that x to the negative 2 power dx. So if I take the derivative of natural log of x again, it's 1 over x dx. If I integrate this, it will be u to the negative 1 divided by negative 1. If I said u, I apologize, but x to the negative 2 power would be x to the negative 1 over negative 1. So plug it into our integration by parts. So we can simplify this, if you wish, to negative 1 over x when we do our substituting. So u times v, negative 1 over x times natural log of x minus the integral negative 1 over x times 1 over x dx, my du. Factor the negative out to the front, make this a plus. I'll have 1 over x squared, or x to the negative 2 power, and we can integrate that using the power rule. And that wraps up 8.5. So again, lots of practice of all our integration rules.